picture that I drew, except I have better colors now. So the idea again is to find this line in two dimensions. It's a line, but in general it'll be some hyperplane that best separates the two sets of points, in the sense that the margin we can put around the line is the widest possible. So what we have is our line here, and we can look at those points for which are closest to this line. And so there will be these 4 points here. And we want to find this line that maximizes this distance to the closest points, because that'll be the one that has the widest margin around it. And so the way we're going to try to figure that out is to parameterize the, in this case, line, in general, a hyperplane. And in general, we can write such a hyperplane as an equation, some vector beta, is a set of points such that beta of x is equal to some constant c. So it's a set of all points beta such that when a set of all points x such that when you dot it with beta, then it's equal to a constant c. And it turns out then that beta is a vector that's perpendicular to the plane. So here's our hyperplane H, and beta is here, and that turns out is perpendicular to H. So we have a beta here perpendicular to the line. We have this little vector r here, which is also perpendicular to the line. And so if you have two vectors that are perpendicular to the same line, or in general to the same hyperplane, well, then they must be parallel. So that means that this little vector here is a multiple of this vector here. So we can write here that this vector r here is the sum alpha times the vector beta.
Hey, sorry, Niels, one question here.
Yeah.
How are we ensuring that beta is perpendicular to the hyperplane unless we are doing a dot product and saying it's equal to 0? Probably.
No, because that's yeah, but it's only when it goes. It's not. It's you see a vector here on the. So let's say we take a vector here on the hyperplane, right? That'll be this vector here.
Yeah.
Yeah, that's not perpendicular to beta.
Okay.
So it's when you if you were to move this hyperplane through the origin, mm-hmm. then beta is perpendicular to it. If you move this, if this is a real hyperplane, a linear hyperplane, then that goes through 0 to the origin. Then it is perpendicular to but it's not perpendicular to vectors here that are on the line. In fact, they all have the same. The dot product all have the same value. You have to be careful that the points on the line, or they're described by vectors that start at the origin, right? So a vector. So a point on the line here that corresponds to this vector here. And that's not perpendicular to beta. So our little r here is a multiple of beta, because these two, this vector here and this vector here, they are parallel in the sense because they are both perpendicular to the same line. So let's try to write this r here as a vector x. So that's a vector that goes from here up to the point. and then the corresponding point on the line. That's what we call A here. So then what we have is that R is X minus A. We have here A, and we have here X, and here's our little R here in between. So R is equal to X minus A. So what can we say then? Well, we can look at alpha. So R was alpha times beta. Alpha times beta is then equal to X minus A. So we now dot this equation here with beta. So take the scale up the dot product of this equation here with beta. Well, I get alpha times beta dot product with itself. That's the norm squared. Beta is equal to beta dot x minus beta dot a. But now a is on the line. So a is one of the points here. That means that beta dot a is equal to c. So this is equal to beta dot x minus beta dot a is c. And so again, I get an equation for alpha here, namely alpha is equal to beta dot x minus c divided by beta all squared. So again, x is one of these points here that are closest to the line. So this is what we call the support vector. So x here is a support vector. Here another support vector would be here. And here would be another support vector. What we get is that this alpha here is can be written in this form. And so the norm of R, which is the norm of alpha times beta, so that'll be the absolute value of alpha times the norm of beta. That'll be the length of this here. Let's just call this mu. So this is the distance from the line of these points that are closest to the line. They all have distance mu given by this formula here. I can plug this into my expression here, and I get the formula that mu is equal to alpha times norm beta, and this was equal to, well, absolute value of alpha is equal to the absolute value of this divided by beta squared. So when I multiply by beta, I cancel one of the two things, so I get that this is equal to the absolute value of beta dot x minus c divided by beta. And then then we start doing this stuff by saying, well, if we scale beta here, so if we take another beta here, which is just a multiple of beta, so we can scale beta here by going up or down, as long as we're just multiplying by a scalar, we'll get a vector that's parallel. And so what happens if we take another vector?
Sorry to interrupt.
Yeah.
This might be a stupid comment, but still, you have written beta dot x equal to c, right?
Yeah.
So why beta dot x minus c is not 0? Why mu is not becoming 0 there at the top when we assume?
Yeah, that's because this is not the same. So yeah, I'm using
or we use, this is a different constant?
I'm using a notation I shouldn't. So let's say that the H is the set of all U such that beta dot U is equal to C. So set of all vectors. So here is a vector U. This vector here will be one of those vectors. X is in my equation here. X is the one of these support points here.
Correct. Vector to point A.
Yeah, I was just using the
Okay. Yeah. Sorry.
wrong notation.
Yeah.
So if I scale beta by some lambda, so instead of looking at beta, look at lambda times beta. And what happens to the equation here? Well, I just multiply the equation by lambda here, and so the equation here just becomes W dot U is equal to lambda times C. So all that happens is that when I scale my beta here, I take a multiple of beta, all that happens is I change the constant here. So if I scale correctly and take a W such that this thing here becomes 1, right? If I take W here, I get alpha times W divided by lambda is so that's equal to, well, let me not do this. Can you still see it?
Yep. Yes.
So if I use this here, I get lambda W. No, sorry. If I multiply this whole thing here by lambda, I get lambda times mu is equal to lambda beta dot x minus lambda b divided by lambda w. So if I choose the, so I can write this as lambda times mu lambda w is equal to w dot x minus lambda c. This lambda c I'll call c prime. And so if I choose the correct lambda here, I can make this equal to 1. I can choose any, this should be a beta. So I can just choose a lambda such that this side here is equal to 1. And so if I do that, I get the equation that 1 is equal to w dot x minus c prime. And so I can write and so what I get here is that w norm w dot mu is equal to 1. That's what I get out of this. So what you can see is that if I want to make mu here as large as possible, that means I want to make this as small as possible. So I want to find a W that satisfies this condition here for all the points, all the support points, all the points that are closer to it, and such that this, the norm of it is as small as possible. Once I get this, I will get that mu is the largest possible. So the condition I get for all the other points here, so I have a data point here, say xi here, so that's another data point. What you get is that for those data points, you have that w dot xi minus c prime is bigger than or equal to 1. And so again, by choosing the direction of beta here, or choosing the direction of w, the right way such that it points in the plus direction. So if these are the ones that have labeled +1, these are the points that have labeled -1. And if the label for xi is yi, so y is ±1, I can achieve that that this by multiplying by yi, I get that this is positive. So I can write this as yi times w dot xi minus c prime is bigger than or equal to 1. So this is just if so this absolute value here is bigger than or equal to 1. Well, this can be, the stuff that's inside can be positive or negative. And if I arrange it such that when it's negative, well, then yi is -1, so I get negative times -1, well, that's positive. And vice versa. If it is positive, then yi is +1. So my problem here to the solution, at least the, what can I say, not the solution, but the mathematical problem that we end up with for this geometric problem is to find w such that w dot xi minus c prime times yi bigger than or equal to 1 for all data points xi, and such that the norm of w is minimal. So this is a convex optimization problem. It's finding the minimum value of w subject to these constraints here. And there are ways to solve this, which we won't go into, but one can formulate this in terms of what's called the dual problem. So the solution here is the same as find numbers alpha 0, alpha 1, up to alpha n minus 1. So there are a number of data points. Capital N. So the dual problem is to find numbers alpha 0 up to alpha n minus 1 that maximizes the sum of the alpha I minus, or is it, I can't remember, it's minus or plus.
And you cannot see the whiteboard because it's coming in front of you. So sorry.
What's that? Is it plus?
No, we cannot see the whiteboards. Okay, now better. Yeah.
Okay. So it's yi, yj, alpha I, alpha j, xi dot xj. So this is I equals 0 to n minus 1. This is I and j. This is double sum such that this is, find these numbers that maximizes this expression. and such that the sum yi alpha I is 0, and the alpha i's are all bigger than or equal to 0. So this is the dual problem to this optimization problem here. And if we can solve this, so if we can find these things in which you can do in many different ways, like taking partial derivatives, put them equal to 0, or some stuff like that, then W, the vector we're looking for over here, simply becomes equal to the sum of alpha I times xi. This just becomes this linear combination of the support vectors, and the alpha I is 0 if xi is not the support vector. So for all the data points that are further away than mu, so whose distance is bigger than mu here, the corresponding coefficient alpha I will be 0. So that's the that is the formulation of the optimization problem that we will use to be able to solve in order to find this this line. And there are ways to do this. I won't go into it, but there are different ways of doing this. It's like a quadratic optimizer can do this, but there are other algorithms that can do this. But we won't go into the actual way of solving this, because that's a lot of math that goes into that. But let's take it from there and expand on the model here. So let me plug in.
Actually, can you talk a little bit about the solution to this problem? Is it's like the gradient descent has some fine tuning in terms of the learning rate and some slowdown as it approaches the minimum. Do those kind of problems? I can't quite see the optimization here, but is it a better optimization than a kind of gradient descent type convergence? Does it converge faster to the solution? Because
no, I mean you don't really. So since it's a constrained optimization, you can't just use gradient descent here, because you have to satisfy these constraints. So what you can do is that there are different number of different algorithms that allow you to do that. But so you can't just so if you start using gradient descent, then you're gonna change one yi at a time. But
I wasn't suggesting using gradient descent. I was wondering if the convergence of these algorithms are better than a gradient descent. I'm not comparing it to the same problem. I'm saying, we have certain problems to worry about there, so in other words, is the determination of the hyperplane a better solved or a better understood optimization problem than, say, the ones we looked at with logistic regression?
Well, I mean, it's not a. I mean, the algorithms are different. But one thing you're trying to maximize something which is well, it's the same problem, but I mean, you probably could use. I mean, the thing is that you have when we're doing gradient descent, you're just trying to find a point where the gradient is 0.
Right.
But that's not enough here, right? Because you still have the constraints involved. So you can't just find a set of alphas
right.
such that the gradient is 0. They won't satisfy the constraints. So it's a constrained optimization problem, which requires different methods to solve. Let me put my headphones.
And also here we still have the problems of high dimensions, right? For example, because you're still searching for a hyperplane in whatever n your feature space is, right?
Yeah, I mean it's a quadratic. So you have quadratic optimizers that can solve this, but if you have too many, so the problem is how it scales with
With the number of feature vectors.
yeah, with the number of data points. Yeah, so if you have very large data sets, you're going to have a lot of alphas.
But you were actually able to cut off the alphas that lay outside the region of U, right?
No, that was beta.
No, I mean the truth is, yeah, that you only get those. The only non-zero alphas are those that correspond to the support vector. So those that correspond to the vectors that are closest to the
Right. So I could have a large number of data points.
What's that?
I could have a large number of data points that lie outside, and they don't.
Yeah, sure, that's right. But I mean, you have to find them, right? You still have to find the ones that. You have to find the ones that. I mean, you have to find the hyperplane that
Yes.
that does it. So it's not so clear.